Okay, working on number 17, we're doing the double integral over the region R of x squared dA. R is the region enclosed by this ellipse, and there are my transformations. So let's take a look at this region first. This is the region bounded by this ellipse. So we have this ellipse here. It's our region R right there. And this is the xy plane, so those are our two variables. And we're going to convert over to the UV plane. So we're going to transform this region into something that hopefully will be nicer. So let's go ahead and take a look real quick at what the transformation is. So what I'll do to figure out the transformation is I'll take this equation, I'm going to replace x with 2u, and then I'm going to replace y with 3v. I'm going to see what sort of equation I get from this. So if I square this, I get 4u squared. I multiply times 9, I get 36u squared. Here I get 9v squared when I square this times 4, so you get 36v squared equals 36. And that's u squared plus v squared is 1, which if I look at that in the UV plane is going to be the unit circle. And this region S, we'll call it, will be much easier to integrate over than this one, because I can use polar coordinates on that. But before I do that, I'm going to transform this integral. So this integral right here is going to be equal to double integral over S. Now x squared is 2u squared, so that's 4u squared. But then I need my Jacobian. So I've got to come in here, I've got to do some partial stuff here in order to finish this out, to get that to get whatever the Jacobian determinant gives me. Reminding you, since I know I did it in the previous problem, but you're looking at note, where is that darn thing? Where do I have it written out? It's note 12.8.3. So what we're going to need to do to get the Jacobian determinant is we're going to need to do the partial of x with respect to u times partial of y with respect to v minus partial x with respect to v times partial y with respect to u. So we need to figure out what that is. The partial of x with respect to u here is going to be 2. Partial of y with respect to v is going to be 3 minus partial of x with respect to v. There is no v here, so that's 0. And this doesn't matter, but this is also 0. So you get 6. So I'm coming back here. I have to say times 6, right? That's my Jacobian determinant. And then with respect to the new area. So that looks like it. I can clean that up a little bit. I can say that's 24 double integral over S of u squared dA. And now I look at this region and I say, all right, well, I'm going to go to polar here. So to go to polar, remember that our polar transformations were things like this. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And that's all great when our variables that we're starting with are x and y. See, here we have u and v, so I can't use x and y, so I'm just going to replace my x with u, my y with v. All right, and those are my transformations. So from that, I know, of course, my theta, to draw this region, has to be between 0 and 2 pi. I know that my r has to be between 0 and 1. And then I rewrite this integral. So I have 24 integral 0 to 2 pi, integral 0 to 1 of u squared, but u is r cosine theta, so r squared cosine squared theta times, now we have that we went to polar, so I always have to have the r, and then dr d theta. And so this becomes 24 integral 0 to 2 pi integral 0 to 1 of r cubed cosine squared theta dr d theta. Just putting my r's together. And I also noticed that my thetas and my r's are split, so I can use that special property right now, and I can do two separate integrals and multiply the answer. So I'm going to say it's 24 integral 0 to 1 of r to the third dr times integral 0 to 2 pi of cosine squared. And I already know that when I do cosine squared, I'm going to convert it to 1 plus cosine 2 theta. And then there's a half there from the formula, and I just pull that out. So that's what I've got to do now. The antiderivative of this, so I have 24 times, the antiderivative of this is 1/4 r to the 4th, evaluated from 0 to 1. So I've got to figure out what that is, times antiderivative here, 1/2, antiderivative 1 is theta, antiderivative cosine 2 theta is plus 1/2 sine 2 theta, evaluating this from 0 to 2 pi. So I've got two evaluations to do, and then I'll just multiply that answer times 24. So I think I can fit this in right here. Get 24. Okay, when I plug in 1 here, I get 1/4. When I plug in 0, I get 0. So I'm just going to have 1/4 minus 0. And then the next one, when I plug in 2 pi, let's see what happens. 2 pi here. Sine of 2 times 2 pi is 4 pi. Sine of 4 pi is 0, so that whole thing zeroes out. I get 2 pi times 1/2, so that's just pi. And then when I plug in 0, I get zeros here. So everything zeroes out, so minus 0. And so this is 24 times 1/4 times pi, which is 6 pi.